Good morning. Yeah. Okay. So I've sort of changed the title a bit because the first title was more of an abstract. What I wanted to emphasize was this idea of a class of abrupt transitions, which let's call them zeroth order. We'll see why I want to call them that. So this work was done mostly with Satyaki and Taposh, who are my PhD students. And some of the analysis which I'll discuss was done with close cooperation with Rajesh Nayak. And there are other collaborators who also we worked with over time. So it's about abrupt transitions in metastable states. So as we all know that sort of first order transitions can supersaturate, they often do. And that's because of the certain nucleation barriers which you always have. And these metastable states are typically these states containing domain walls, if you have an Ising model kind of a picture. And they're essentially kind of so they of course don't belong to the global minimum of the free energy, they belong to a local minimum of the free energy. And essentially the belief is that of course they are not equilibrium states, so if you sort of wait long enough, then you'll access the global free energy minimum. So in that sense, metastability is a kinetics issue. So, but most of these arguments are based on our understanding of short-range systems like the Ising model or Leonard-Jones fluids and things like that. And the claim, or what I want to emphasize in this talk, is the fact that for other systems which are long-ranged and very commonly encountered systems, some of the ideas actually sort of seem to break down. And so this is a summary of the argument which I want to present here. So many commonly encountered thermally induced abrupt transitions, which means essentially entropy-driven transitions, fluctuation-driven transitions, are necessarily hysteretic. So this is something which is found empirically. And these metastable states are, unlike these domain wall-like states, are, if you like, translationally invariant and have infinitely long lifetimes. And so these, I will argue, should be sort of thought of as belonging to a different universality class, a mean field. They should be called mean field-like. And that is because the transition is actually sort of controlled by spinodal singularities. And what I'll show is that we've done experiments which sort of show that you get critical slowing down, critical opalescence, critical dynamics in a first order phase transition. Okay. And as I said, I just want to emphasize this is something which is very common, and it's more the rule than the exception if you are, especially if you are a material scientist. So for instance, there are a lot of transition metal oxides which show, so this is one curve corresponds to the cooling cycle, the other to the heating cycle, and you always see hysteresis regardless of how slow you do this. So this is really what is always observed. There are other systems, so there's just to give an example of various systems. So there's some organic compounds, charge density wave materials, spin density wave materials. Then you have a lot of intermetallics like Heusler compounds, martensites. So they all show these, they are all thermally driven transitions, and they all show finite hysteresis loops. And shape memory alloys. So again, for instance, this diagram sort of shows what is the width of the hysteresis loop for this combination of these three metals. So the reason I feel why this is so common, I think many people would probably agree, is that, or at least whatever I showed in these systems, what is common is that there's an electronic transition. These are correlated electron systems. And there's an electronic transition, but the transition has a strong polaronic coupling due to some reason. Could be piles kind of instability or something. And that leads to a structural transition. And the structural transition leads to long-range strain fields. And once you have long-range strain fields, so these are not infinitely ranged. So they're long but finite ranged strain fields. Then possibly mean field physics could result. And if you have mean field physics, then you can have spinodal singularity and criticality. So that's the argument. Okay. So this is just a cartoon to sort of talk about two catastrophic conventions of abrupt phase transitions. You can talk about a delay convention or a Maxwell construction. So of course, what you have normally is a Maxwell construction. So of course, what this denotes are the two competing free energy minima drawn in the order parameter. This acts as the order parameter. And so they compete. And the first order transition is supposed to happen when these two minima are of equal height. But this is still a metastable state here. But then you sort of, via Maxwell construction, fudge the free energy such that the system only is constrained to the global minimum always. On the other hand, you can also have a delay convention. So if there were no fluctuations in the system, or if the fluctuations are somehow suppressed, of course, because this involves a barrier crossing, so then you can actually persist right up to in the worst case scenario, you can persist right up to the point of instability where this minimum becomes an inflection point. And this inflection point, when the system reaches this, is called the spinodal. And as you can see, so the argument is that as you can see that here the first and the second derivative of the free energies diverge, is zero. So the susceptibility would diverge in the same sense, roughly in the same sense as it does in the case of a critical transition. So you would have various, so yeah, you will have features of criticality because of that. So this is again what I've said. So you can have delay convention, and so in Maxwell construction, of course, you sort of by fiat make sure that there's no hysteresis. And these transitions are naturally called zeroth order in the sense, yeah, if you like, because the free energy itself is discontinuous, not its first derivative. Okay. So, but the problem is that this is fine, you can always supersaturate systems. But one would normally expect that because if you have, unless you're at zero temperature or infinitely long range interactions, you would expect that as soon as the barrier height becomes some multiple of kBt, there will be in any case a thermally induced transition. So the spinodal singularity is more of, meaning it's abstract and it should generally not be accessible. So the argument which I'm trying to make here, or what we observe experimentally, is that although you don't see perfect divergence, but the transition does indeed seem to be controlled by these spinodal singularities. I have studied two systems, one of them I'll describe here in detail. And I guess most of these systems which I showed earlier should possibly follow this, of course, with, yeah. Yes, as I said, so yeah, so normally the first order transition occurs through nucleation. Yeah, but if you have a spinodal transition, then of course it's like it's just rolling down the hill. Okay, let me just, yeah, so this is what I've said, that these are the two spinodal points where the two derivatives, okay, yeah, vanish and the susceptibility would diverge. So yeah, so that's what I've said already. Okay, so coming to our experiment, so we have studied these abrupt transitions in V2O3. The material details are not important. The fact that you can see some latent heat and there's a sharp abrupt transition. And what we do is measure resistance. So, and you can think of the order parameter as say so there's an insulator to metal transition. So you can think of the order parameter as the fraction of the insulating phase in the system, if you like. It's some kind of phenomenological order parameter. And if you're measuring resistance, so it's like measuring the spatially averaged order parameter, which is like a k equal to 0 Fourier mode of this order parameter. So basically, you're measuring the k equal to 0 Fourier mode in our experiments. Yeah, okay, so this is something which, yeah, I think most people are familiar with. So yeah, essentially you can describe, depending on the symmetry, you can describe some dynamical equation. So let's say, if it's non-conserved, then of course this is the evolution equation. And around the spinodals, you can sort of phi s is the value of the order parameter at the spinodal. Then you can Taylor expand. And the second derivative is just the non-local susceptibility. And then I can go to Fourier space. And in the linearized version of this, the linearized theory, I can easily write down the expression for phase ordering and the autocorrelation. So the idea being that, yeah, and what I measure in experiments, as I said, is k equal to 0 mode. So what I measure in experiment is this average evolution of the order parameter k equal to 0 mode of the full order parameter, which is this, and the autocorrelation. Okay, and the expectation being that this relaxation time should diverge as the susceptibility, and the variance itself should also diverge. So that's what I'll try to show in the experiments. So yeah, that's what I've said. So these are some experiments where you essentially shock heat and quench cool the system too close to the spinodal or just outside the spinodal, and then you observe some kind of an evolution, and you can fit some exponential time dependence, and you can see that this is a divergence of this relaxation time. And again, we've also measured the fluctuations. So you can do these noise measurements where you essentially just measure the resistance time series. And yeah, okay, so it's hard to sort of get any signatures of non-Gaussianity, but of course you can't say for sure. And if you look at the power spectral density of fluctuations, then you can see that at the two transitions, which are these two curves, the spectral rate seems to shift to lower frequencies, which is again a signature of critical slowing down. And one can also say the same thing in time domain. And so this, which is basically the time scale of the autocorrelation relaxation, also seems to grow at the two spinodals. This is again evidence of critical slowing down. And similarly, you can look at order parameter variance, which also seems to grow at the transitions. So I should emphasize that one of them is for cooling, one of them is for heating. So you see symmetrically, so one side you see transition at around 162, the other side 152 or so, and the other side you see a transition at 162. So you actually see two transitions, which is consistent with the picture of the spinodal, depending on whether you're cooling or heating. Okay, so this, let me just not get into this. So you can also, yeah, because there's a hysteresis, you can sort of drive the system at different rates, and you see the area of the hysteresis loop also scales, and the scaling exponent is also the mean field exponent 2/3. So this also suggests the same physics that essentially is the mean field physics, which sort of controls it. So the idea is that, of course, because you have a finite temperature system and your system at finite temperature and the finite range system, so these singularities may actually not be true singularities, but they, in the sense, these divergences are not true divergences. But in any case, it seems that the spinodal transition, the spinodal singularity does control the transition in the sense that at least you see it rounds off. So it's like a finite size effect. The fact that you have a finite range of interactions is roughly like a finite size effect. It rounds off the sort of a transition, but still the singularity seems, is very much sort of felt by the system. Okay, so I'll just very quickly, just maybe just 10, 20 seconds, yeah, just to say that these are similar ideas also used in complexity science, where people basically talk about things like, yeah, you can, so essentially whenever you have catastrophic failures in various kind of systems, it could be epileptic seizures or, whatever, earthquakes. So these, whatever I've discussed, are also actually sort of talked about in terms of some signatures of an imminent catastrophe. And essentially the physics which people discuss is very, very similar. Okay, so anyway, so that's, sorry about overshooting.